All right. Hello, everybody. Previously, on previous lecture, we deduced the dynamics, the dynamical laws of in our formalism, right? So we deduced that the dynamics of the system is governed by a Hamiltonian that generates a unitary evolution operator, right, which gives us Hilbert space representation of passage of time, basically. And we saw how it should be implemented in our formulas, right, to describe the by probabilities. Then we went to figure out how to represent composite systems. So we got our Hilbert space, outer product of Hilbert spaces, right, to represent the space of the composite system. And we discussed what happens when those systems interact with each other, which led us to discovery or to establishing the link between observables, that is, things that could be measured by with measuring devices, and Hermitian operators, which could play a role of Hamiltonian, right? And in particular, they can compose the interaction term in the Hamiltonian. So that was, which gives us some clues that perhaps measuring devices we were using all along could be seen as essentially some kind of a quantum system, special kind of quantum system, most likely coupled to a specific operator that would represent an observable. And this is how you realize measurement, maybe. We haven't checked that yet, but this is like a hypothesis that comes up quite naturally once you investigate all the facts. So we are almost done with our deduction, because we have our those by probabilities. We have the ability to construct models. Our understanding of Hilbert space representation. We know how to represent dynamics, how to represent interactions and stuff like that, but there is still one piece missing. A couple of lectures ago, when we started to deduce the formalism from the phenomenological observations, we identified that by probabilities, we identified the bitrajectory picture in the sense that the by probabilities associated with a single, one specific observable, they actually are, they are extension or restrictions of a master distribution, master measure on space of bitrajectories, right? So there is this bitrajectory measure. It gives us by probabilities, and but only those. I mean, back then we identified this relation only for the case when there is only one observable present. But that's not enough, because in quantum mechanics there are infinitely many observables. So this is very specific restriction to talk about only a single one. So the thing that we are missing and want to fill in the gap is so what about those by probabilities associated with many observables? Is there a master bitrajectory measure they are restriction of? Okay, so is there, in other words, what is the true master object of our formalism? And we want to identify this guy. But to do this, we'll have to do some formal constructions. Okay? So we have to increase the level of abstraction right now. Okay, so to jump out of the phenomenological mindset and just play with our formalism in its abstract glory. Okay, so with this construction, it might seem random what I'm doing right now, but believe me, it will lead to something interesting. So, okay, let us recall that previously, when we were deducing the form of dynamical law, we grabbed on. I mean, our entry point was a observation that passage of time was basically boiled down to the change of basis, okay, in Hilbert space. So bear this in mind, that basis and changing of them is kind of useful in this formalism. So let's start from, let's take our Hilbert space, our system Hilbert space, HS, okay. We also have a Hamiltonian for our system. And let's pick a reference basis. Pick a reference basis in our space. Let's call it E. It will be a set consisting of vectors with index eta. These vectors sit in our space, and they are such that eta goes from 1 to D, where D is a dimension of our Hilbert space. And yeah, it's an orthonormal basis, eta prime. Okay, so we just pick some basis. That's very simple. We can index it from 1 to D. And now, okay, so we have our reference basis. To select an arbitrary fine-grained observable K. Okay. So for this observable, we have we have projection operators. Let's say at time 0, indexed by K. And since it is a fine-grained observable, so this is a rank 1 projector. So there is so we have our ket bra. The projector is ket bra, such that those states form another basis. Sorry, vectors. Let's not get ahead of ourselves here. K belong to the spectrum of observable, capital K, and they are orthonormal. K prime, delta K prime. Okay, so now we have our reference basis, and we have bases associated with observable. Of course, they are connected via some unitary transformation. Unitary basis transformation. Right, so we can always find a transformation that allows us to go from K0 to E, right? Or in other words, we can write the following. I'll explain shortly what this mysterious inscription means. So this is maybe let me write to distinguish it from tuples. It's like a vector notation. So this is like a scalar product of two vectors, or in more explicit formula, alpha phi alpha. Okay. So this guy is one of the belongs to E basis. And we want to say that this produces us K of theta. All right, so let me explain what I'm doing here. So this guy here, this operator, is a unitary operator. And I choose here to represent it with a, maybe it's kind of fancy way to represent it, but in every Hilbert space, okay, that there is, if you use a little bit more advanced mathematics here, group theory in particular, you can show that in every Hilbert space, unitary operators can be like broken down into, can be shown to be generated by a special set of Hermitian operators, right? It's like Hamiltonian generates unitary transformations that change time in our system, right? So there is a like general formula that you can any unitary transformation can be parameterized like this. So these T operators, so T operators, T alpha, and alpha goes from 1 to d square minus 1. I'm sorry. Forgot to turn off the sound. So these guys are Lie algebra generators, okay? So, and there is d squared, so this is dimension of the Hilbert space, d squared minus 1 of them. And when you combine them with a vector, a collection of real coordinates, on the hypersphere, as so hypersphere of dimension d squared minus 1. So this is like all right, higher sphere that's higher dimension than 3. All right, you calculate something like this, and you can parameterize any unitary transformation in this way. You can parameterize it in many ways, but this one I like it because it's it's like time evolution. The dynamical law is like there is Hamiltonian, that's a generator times time. This is what gives you the transformation, and here is just generalization of that. So to give you example. So if you take d equals 2, so a qubit Hilbert space, those generators, which they are not unique, okay? There are many ways to pick those generators, but one of the possibilities is just to select a sigma poly matrices. Okay. So for dimension 2, you have 4 minus 1, so 3. There are 3 generators, Hermitian generators, and in this case you can just pick poly matrices. So if you take, I'm sure you know this, right? It's like phi x times plus phi y sigma y plus phi z sigma z. Okay, from like basic standard quantum mechanics textbooks, if you did anything with qubits, right, you know that this is how you represent any unitary transformations. In higher dimensions, of course, there is there's more generators in three dimensions. You can, for example, pick Gell-Mann matrices, or there are other many ways to represent it, depending on what you want. Here, you don't have to think too much about it. Okay, which generators you pick. I just want to have this nice symmetry between evolution in time and this spatial evolution, right? Where you have those 5 coordinates, which like tell you, okay, what is this shift in basis? Okay, but there is one more nuance here, because if you want to have a transformation between 2 bases, it's not entirely unique, because there is always a freedom to choose how do you assign the indices between bases. So here we have eta indices that go from 1 to d, and in basis k you have basically indices k that number your basis elements. And now you have unitary transformation that transforms basis E to basis K, but you have this freedom to choose, okay, but what is the permutation of indices? How do you map indices from one basis to indices in the other basis? And there's a freedom to choose that. And this function here, this mapping here, so this K here means that it's a map from a set of indices from 1 to d to omega k. All right. So we fix that. We choose one of the permutations available, and then we can find the phi that actually realizes this specific transformation. So that would be a so we chose our reference basis, and now any fine grain observable is basically one unitary transformation away from this reference basis. And in general, that was what, 3? Okay, so that's 4. General observables F. So if you take any observable that's not necessarily fine grain, how grained it is, it's kind of it's whatever, unspecified. But you can still find a transformation that brings you from the projectors onto etas, onto elements of this basis, to projectors onto eigenspaces of operator F. So it's not okay. So to find the coordinates and the mapping of indices, you can always do this by solving a corresponding eigenproblem. So set of coordinates, parameterizing transformation, and mapping. Let's call this mapping F. Goes from etas to omega f, and it's such that, so you take omega f prime projectors minus f eta 1 times e I t times f acting on vector eta equals 0. So this is eigen problem, right? Eigen values, eigen vectors, and once you solve it, you can. It's probably not very easy, typically, but to extract the this vector phi and stuff like that. But this is not something we will actually be doing in practice. It's just to recognize that there is this parametrization. So there is transformations in time and transformations in space. So we have like space-time transformation, which like determines time and observables. Okay, it parameterizes time and observables. It's kind of abstract, but there will be payoff for that. So 5. So we have this. So we covered the spatial part, and now combine time and space. So if you combine the dynamical law in your system generated by Hamiltonian of the system with these basis transformations, you can represent any arbitrary projector associated with any observable f prime. You can represent such a fellow. So this delta here is to cover the cover possibility that f is not perfectly fine-grained. There is some degeneracy, and you have I, H, S, T. So this is the time. E, I. So this is the space. It's projected onto a reference basis, and you have a vectors to distinguish them from tuples. Which is equals to shorthand notation to denote this guy f prime f. So this is a projection operator. Okay, so let's call this guy P eta. All right. So rather than indexing it with f, so observable in time, we have one space-time index, time and the coordinates on the hypersphere. That corresponds to what orientation of a basis. Okay, so that was a lot of information to digest. So again, to summarize this, basically a different. So what this underlines is that change in time is a rotation of basis, change of basis, but also change of observable is like a change of basis. So we can just combine them two and have one space-time parametrization that gives you a choice of time and choice of basis. That's, you can like manipulate it in some, like on some path or whatever. And now we can use those guys. So now we can take those projection operators parameterized by these space-time coordinates and define with them a new type of biprobabilities. Let's call them system biprobabilities. And like our standard biprobabilities are associated with a sequence of times and sequence of observables, and they have initial time and initial condition in the form of density matrix, right? So now we want to define biprobabilities that are indexed not by observables and time, but indexed by those space-time coordinates. Okay. So they will be biprobabilities that are not associated with any specific observable or any initial condition. They are just very agnostic of that. They are like, that's why they are system biprobabilities. They are like very pure in this sense. No choices from outside. So you take Q. So let me Tn by n T1 by 1 conditioned by T0 phi 0, and they are eta vector. So this is the disadvantage of not using a printed medium, because usually if I want to denote tuple in PDF, I just do boldface, okay, but I cannot do it with handwriting. So I would love to write here a tuple of etas, but now there is a confusion between between this vector and the tuple. Okay, so bear with me. If the arrow is a proper arrow, so like this, it's a vector, and when it's this half arrow, it's a tuple. Okay, I hope you won't get lost too quickly with that. -1, and those guys trace product J n to 0 p j phi j eta j plus product from 0 to n phi j eta j. Okay, so it's very similar to standard biprobabilities, but there is no row in the beginning. You have just, and you're indexing by those space-time coordinates, right? But things to note, you have causality, right? Because of trace, cyclic property of trace. So the last guys are, this by sequence meets at the very end, okay, and also at the beginning. So this guy here is not naturally proportional to eta n plus eta n minus and eta 0 plus eta 0 minus, okay? Because the projectors have to, yeah, they meet each other and, and produce deltas. Just a thing to know. And okay, so these guys are very abstract, but they are manifestly like in this hierarchy of objects. Let's call it, so which objects comes from which. So these guys, by system by probabilities, they are above their observable associated cousins, okay, in this hierarchy. Why? Because you can obtain by probability associated with observables as a convex combination of system by probabilities, which we can just write down here. So our good friends observable associated by probabilities, they can be expressed as, here's my formula. This is how you obtain them from system by probabilities. So you sum over tuples of etas and eta 0. You take here a restriction, delta fj eta plus j, fj plus fj of eta j minus fj minus. Okay, so these mappings here, they are corresponding to this kind of solution to this kind of eigen problem for observable fj. Okay. All right. So here you have observable fj, right? So there is a mapping of indices you find from solving the eigen problem, and there will be also the coordinate phi j corresponding to this observable. So you get this times q tn E1 phi 1, right? So here you have eigenvalues from the eigen problem, and here you have a coordinate corresponding to eigenvector, conditioned by T0 phi 0 of eta tuple eta 0 times rho eta 0. So the new element that comes up is rho, which again you obtained it from solving the corresponding eigen problem. Rho eta times 1. Okay, this is how you get rho and how you get this coordinate, right? Or in other words, you can write that rho T0 is T1 to D rho eta P T0 phi 0. which amounts to saying this, okay? So in other words, those guys that associated with observables, the guys that are actually connected to phenomenology directly, oh, maybe indirectly, but more directly than those new abstract system by probabilities, they are obtained from those guys, okay? From those guys we just introduced. So they, system by probabilities are master objects with respect to observable associated by probabilities, but only through those observable associated by probabilities, system by probabilities have connection to phenomenology. Okay, so they are all useful in their, they are integral elements of the whole formalism, but these guys are above these guys. Okay. So once we establish that, now the thing we want to say, can we find the master by trajectory measure that those guys extend into, okay? In other words, master trajectory in other words, can we write the following thing by one then we say that this guy is a double integral products zero eta j plus eta plus tj phi j delta eta j minus eta minus times q is a functional where this guy is a complex value measure on a space of by trajectories, b trajectory, by trajectory in the sense that you take a r times hypersphere element from this, so t phi mapped on the pair of functions which belong to 1D times 1D. Okay, so it's by trajectories rather by fields, maybe because it has a time component and spatial component, right? So does this thing actually exist? Okay, can we do a generalized Kolmogorov extension theorem for those system by probabilities and extend them into this master measure? Okay, so this is if we can give an answer to this question, preferably positive answer, then this guy would be what we would call the true master object of the formalism, because it would in fact would be the source of everything else in the formalism, okay? Because it would, through discrete restriction, it would give us system by probabilities, which then give us observable associated by probabilities, which then give us whatever else you want, okay? So we found this kind of relation previously in the case of only one observable, right? So maybe just, okay, so let's use the same proof, the same mathematical theorem to determine the existence of this guy. However, there is a problem here. There are, for several non-trivial reasons, we cannot simply use the previous theorem and apply it to this case, okay? I won't get into details why. If you want to know why, you can check out one of our papers on this specific topic. But in an absence of this formal mathematical proof, we still came up with a argument. I feel it's a strong argument, although I don't really understand all the maths involved in yet. Maybe someday I will understand it. And this argument is basically you can calculate the characteristic function for this hypothetical measure Q, okay? And you can show that this characteristic function is a well-behaved object, okay? So the argument is that if the characteristic function of measure is well-behaved, nothing explodes, everything is nice and tidy, then there shouldn't be anything wrong with the underlying measure, okay? So this is like a provisional argument, but I think it's kind of strong. I won't go into details about the form of this characteristic function. You can check it out in the paper if you really want, but it's not super necessary to talk about it. The thing I want to underline here that the idea to using those space-time coordinates, right, that you extract time and this other transformation, unitary transformation, this is actually informed. This choice is informed by the form of this characteristic function, okay? Because you see, one thing to notice. Where is it? One thing to notice here. Look, this is so we split the basis the observable transformation from time. Okay, we split them apart, but the composition of two unitary transformation is just another unitary transformation. You could even represent it with some new set of coordinates on the hypersphere. You could just gobble up the Hamiltonian and time into one big transformation. Okay, so you could equally well, seemingly, just define by probabilities that just indexed by unitary transformation, just unitary transformation, some abstract unitary transformations with sequence of U's. So you could you could try to talk about like Q, that's UN, U1 conditioned by some U0, something like this. You could do that. So why this split into time and space is preferable than this guy? Well, the reason why the split is special comes from okay, can you prove the extension theorem? Can you find the master measure for these guys, or can you find them for these guys? Okay, because if you did the extension theorem for these guys, then you would have your bi-trajectory that's functions of unitary transformation, okay? So we would have something quite strange, perhaps, right? But then the rub is, can you find an argument why the measure on the space of bitrajectories over unitary transformations actually exists? And as far as we know at the moment, this split here is actually crucial. For these guys, yes, we have an argument, but for just this completely like abstract, amorphous sequences of unitaries is just, I don't know what to do there, okay? It seems that there has to be a component that brings some ordering into the whole problem. Okay, there has to be, time is a good thing that orders what happens. First you have this basis, then you have second follow-up time, you have another basis, and so on and so forth. This seems to be crucial. But all in all, the conclusion is that this guy most likely exists. Okay, the formal proof pending, but this strong indications that it does exist, and you have those bitrajectories on bifields maybe because it have spatial and time component, and a couple of things to. Okay. Okay, so these guys exist. They would be the candidate for the true master object. In fact, they are the true master object. But let's for a second go back, because we had this bi-trajectory measure for the case of single observable. Okay, so that guy has to be related somehow to this fellow here. And of course, you can imagine what's going on here, since you want to talk about a bitrajectories that represent a single selected observable, but that should boil down to basically fixing this coordinate here, right? Then it would just kind of restriction of your whole space of bitrajectories. But it's not actually formal, it's not actually restriction, it's something that's called a pushback, push forward measure, or in more plain words, is a change of variables. Okay, so you have a measure Q without any indices. That's a measure on space of these by trajectories, and you want to change the variables. You want to talk about by trajectories where phi is fixed. Okay, it's just only time component remains. So to make it more formal, the relation between what's that? Between Q eta plus eta minus and QF.
Can we think about it maybe in terms of like in the general in the language of differential geometry as moving along along the flow of some killing vector field, something like this?
I think there is some very strong connection to what you are saying. This is what I was trying to find and figure out, because I believe the true formal proof of the existence of these guys, the true proof of the extension theorem, can be found when you go to this kind of differential geometry, because it's like I can tell you about it maybe later, because I don't know how other listeners will react to this, but I believe there is some real this is the way forward, okay, to finding this formal proofs, and this is like most likely the tangent spaces are the key, and this is something like that. Yes, I think so. Although I am not an expert here yet. Okay, I'm still learning about that. But most likely there is a strong connection, because you have here group of unitary transformations, and you have generators. This is like a algebra. Spans the tangent space. There is you have good intuition here, I believe. Okay, there is a lot stuff that's connected like that. But to show this variables change, I think like the most evocative formula you can write is so if we take a by probability that is associated with certain observable f, only one observable f, okay? Yeah, let's say 0. So we showed that those guys extend into this by probability, okay? So on one hand, you can write that this is nothing else than restriction plus at time tj. Okay, this is just a time-dependent trajectory because the orientation of basis is fixed. Fj minus Fj tj. Okay, and here sits this guy, and you integrate. Okay, so that would be what we saw a couple of lectures before. But on the other hand, we have our system by probabilities, which we know how to express observable associated by probability through them. So we can also write that this equals, I need more room here, unfortunately, a restriction on the true master, which is, it's kind of more complicated formula here, will come up. So bear with me. Delta J plus Fj. So this is mapping, okay, from eigenproblem. Eta plus, this is the value of by trajectory at time tj and the corresponding coordinate. Boom. So this you can recognize this, what's happening here. Okay, this goes to this Fj minus Fj eta minus, of course, Ij. Yeah, but there is one more thing, because it's also there is initial condition here, which also comes up when you do the full true master, and this you can write eta 0. But it's one way to write it. Delta eta 0 eta plus 0 y0 minus and the true master. So this is and formally this is a change of variables for measures, okay, or push forward measure of push back, depending on your point of view. So this guy is related to this guy, explicitly in this way, but what's happening here, you're just changing a variables, okay? Change of variables from those eta by trajectory, which space-time dependence, to one that where is space dependence is fixed to one specific point, one specific coordinate. Yes, so still the master relation is preserved, right? Because you obtain QF from Q without any indices by, it goes from Q to QF, but other way around you cannot do this, right? So it's actually the true master is this guy. And yeah, before we go to break, so to summarize, so this is a true master. It is in this formalism. This is basically this Q eta plus eta minus is a thing that is synonymous with the quantum system, because quantum system, as we saw in our deduction, is basically defined by a pair of Hilbert space and the Hamiltonian that generates its dynamics. And this guy, Q eta plus minus, is also generated by this pair. It's generated by this pair in the sense that if you give me Hilbert space and the Hamiltonian, I can, I can compute all these guys and assuming the extension theorem works, right? I can obtain I can extend them into this true master. So in this sense, it's generated by this pair. The system is identified by the pair, so they are the same. Okay, and in fact, anything you would like to ask your system of, anything you want to calculate, probabilities of measurements, whatever else, any by probability associated with any observables, you just obtain them from this guy. This guy is the alpha and the omega. Okay, it gives you everything. It's a true master object of the formalism, and the thing that can be synonymous with the system itself. Okay, and this is basically, we are done. This is the end of the journey in like most minimal way. Okay, we deduce the formalism. So this is what the formalism is. So we started from phenomenological observations. We found out that it's not a that it's not a classical theory we're looking at, because we cannot find we cannot map everything onto stochastic process. So unitrajectory theory is not unitrajectory theory for sure. We discovered that it has to be bitrajectory theory, right? And bitrajectory theories are basically governed by this bitrajectory measures, which are generated, i.e., can be models are built by giving a Hilbert space and the Hamiltonian living in this Hilbert space. Those two guys, this is how you build models of your systems. Okay? Non-classical models, quantum models even. Okay. So now let's take a couple of minutes break, and after that, let's summarize. Okay? Let us look from above on everything and compare, contrast with a standard formalism. Let's see where we at, where are we standing on this whole stuff. Did we solve the measurement problem, for example? Or is a measurement problem still a thing? We'll see. Okay, so 5 minutes break. So it was a little bit boring, I know, but it's I don't know how to make it more exciting, this thing. It's just at some point you have to start inventing the formal inscriptions. That's all there is.
No, the long formulas are maybe not the most pleasant thing to look at, but
yes,
they are necessary.
Yes, yes, yes. And the thing you add about the differential geometry, it's so maybe I can sketch the issue. So okay, let me. Okay, so this. So by probability, that's indexed by just the unitary transformation. So you take your projectors on this reference basis, which you choose arbitrarily, of course, and you just sandwich them with unitary U1, 2, 3, and so on, and you stack them into this form and just take a trace. This is a by probability. Okay, but now if you want to consider something like extension theorem. So the extension theorem is like you want to make, you want to go to the limit where the number of arguments just becomes infinitely dense. This is what you're trying to do. But if you think about this, okay, what does it mean to make it? It's not just increasing n, because I have here like a sequence of n elements, and I can increase n by like adding more on the on the end, adding more on the beginning, or put something in the inside. There are like a couple of choices that you can try to make here, right? And this is depending on what you are doing here. This affects how you the formal proof that we created, that we used for a single observable, because the idea is like okay, to show this extension theorem in the previous case of single observable, we use the fact that when you make the time grid very dense, you have this like small, every time steps become very small, and you can like essentially invoke like Zeno kind of calculations, right? Because you had your transformations were actually parameterized by time, so you can do like Taylor expansion around the small increases, and you go from there, right? So if you want to deploy this kind of proof onto this kind of abstract situation, you need this something that would correspond to the time grid that gets more dense, so that you have small increases, so that you can like do the expansion around small increases, right? So essentially just writing down this kind of by probability with n transformations just doesn't have enough structure. But you can do something clever here, because you could just take your space of unitary transformations, which is a Lie group formally, and you can define a path on this space, path of transformations. Okay, like with time, you have this kind of path, right? You have e to I h times t. It defines a path on this space of transformations, right? So you could take some path that's not necessarily given by time, but something arbitrary, some path. And at the moment you choose any path, you can immediately find the next, you can find a master measure on by trajectories on this path, essentially, okay? So when you have a path, you can deploy the same kind of proof that we used for time, okay? But the problem is that there is no guiding. What are those paths? What to choose? There are infinitely many choices here. You can stitch paths. You can like loop them around, do what, and this is like too many options. Okay, and this is the problematic thing. And it seems that the split into this kind of thing, like in some way fixes it, because it gives you maybe it gives you some order to the paths you can choose, and maybe then but it's still, there are still kinks there.
But from the mathematical point of view, there's nothing special about this first argument, which would tell us that it somehow plays the role of time versus the vector of coordinates, which we then interpret as this hypersurface. Because, I mean, the times that the n's take real values, and the coordinates of this vector phi n are also real values, right?
Yes,
so,
yes.
So we just,
yes,
it's our interpretation that this path given by this first argument is like time propagation or something.
Yes. Okay. Yeah. So this is, this time space, but this is just unitary. You could write it as 1 e to I t and some phi prime, right? Yeah, of course. But then you are here. This is where you end up, basically. And there is this issue with, okay, the path on this abstract space, where it goes, what is the direction? Does it have any direction? What's going on? And but when you do this split, this is it's special in the sense that there is this characteristic function I talked about. This characteristic function uses this split, specific split, but not something else. Most definitely, you cannot like smear together time and this basis transformation. But it's very specific about that. Okay. So most likely there is something to this this space-time split specifically. There is something in it. So some physics comes in here, because from mathematical point of view, like you said, this is just arbitrary choice. Yeah, and perhaps it means that for arbitrary choices there is no extension theorem. There is no master measure for arbitrary choices. But the physics tells us, because this characteristic function is actually a dynamical map that you know from open systems. Okay, but so it comes from physics, this split. Okay, and it's special. Or you could say maybe this is the only way to achieve the extension. That's why physics use it. Who knows, right? But it is very interesting, and I would love to like understand it much better. And I think some differential geometry is in order, because you have Lie groups, generators on Lie groups, paths on Lie groups. This is all, group differential geometry stuff essentially. And but I just don't know enough about it to really get into it, because you also have it's paths, tangent spaces, but you have now measures on it, not really measures on it, but you have bi-trajectories on it and measures on those bi. So it's like it's stacked so much, it's like ooh. And what is arbitrary choice? What can be like mixed? I mean, I just don't know enough about this. But I think it's a cute mathematical problem, which I don't know how to solve yet. But it would be, I would be very surprised if this didn't work and if this guy didn't exist. It just wouldn't make any sense to me. It just, and this characteristic function argument, I think it is really strong. Okay, it is really strong. So I don't know how strong, because I don't understand the maths behind it, but it's like it's no accident. Okay, that characteristic function is well behaved. CPTP map. Okay, so yeah. Okay. So maybe let's let's carry on. We have 45 minutes. And I will try to be succinct here and write very simple formulas only to do the summary. So 10 summary of the deduced formalism. Formalism. Yeah, so again, if someone gives us H Hilbert space, sorry, in Hamiltonian, this generates for us bi-trajectory measure, which is a master object of everything. It gives you everything. Everything else you could do in your theory. And you have T phi. These are the bi-trajectories, right? Phi. So I thought that before we start thinking about what actually you can do with this formalism, I think the good place to start is like to maybe like compare it with the standard formalism, okay, and see what are the differences, because ultimately we expect there will be some differences. I mean, it's like Newtonian versus Hamilton mechanics, right? The formalisms are very different. Interpretations are very different. Explanations are very different then, but they are still formalisms of the same theory. So there is they agree at something, okay? Like there are some predictions that you make with both implementations, and they agree on that. Okay, there is it's not like every single element of each of those formalisms have to have something that's corresponding to something in the other formalism, but there should be some, something they agree on, right? To make sure that this is still the same theory, not some different theory, right? So let's compare it with versus standards formalism. So like, I think that the most basic and most striking the striking difference is that, in standard formalism, we have this dichotomic modes of description, right? One mode for when the measurements when observers are involved, the other mode, which we tend to think like the objective description of what's going on, although this is like, that it represents reality. This is like extra bit. You don't have to attach it there, but typically people do. And this without observers mode, right? We know standard quantum mechanics. You describe your system in terms of states, right? You have some raw states, row of T, which is given by in Schrödinger picture specifically. So a density matrix that changes in time, according to Hamiltonian, the dynamical law tells you how it changes in time. And this is like, when we think about standard quantum mechanics, we think in terms of states. This is how usually we do it. And like the first thing to observe here is that this row, this operator in bi-trajectory formalism, it has no meaning. I mean, it doesn't have any specific purpose. We can recognize here although this is a Schrodinger row in a Schrodinger picture, that if we write the row in a Heisenberg picture, that we would recognize in it a Hilbert space representation of initial condition in a way by probability formalism. So this thing, it's not really, states are not really a thing in by trajectory formalism. All right, this is like the most basic observation here. So does this mean that we have some disagreement between those two formalisms? Where is this part where they agree on something? Okay, so if they don't agree on this very basic step, right? The thing, the master object of standard formalism, the state is just completely, it's essentially absent in by trajectory. So how can they agree on anything then? Well, if you think about it for a minute, it's not like even if in realist interpretations of standard formalism, and those interpretations when you really attach an objective reality to states, they are real objects, they mean something, and so on and so forth. You don't really make any predictions with state alone, right? It's never, it's not like you measure states. It's not like you systems when two quantum systems interact with each other, they sniff out their states or something like that. It's never like this, right? The measurements, you have to take state and plug it into Born rule, for example. Or if you want to have sequential measurement, you plug it into appropriate formula. You can think of it that there is a collapse on the way or something like that, but it's like the state, the naked bare state is not really a thing that corresponds, even in standard formalism, to some testable predictions. This is what I want to say. Okay, so what are the testable predictions that you can make with standard formalism? Okay, so you can start to list things like, the probability of obtaining certain result in a measurement. So Born rule you would apply Born rule here. Okay, so sequential measurements. The other stuff, and maybe I can come up with things like linear response theory, where I calculate certain correlation function, where I put in state at some point to the formula, but I put a lot of other things and calculate some specific correlation function, which then gives me something that's a testable prediction. Because, this is like, I do a measurement of one observable, but it is explained by a certain correlation function that I calculate using the state. But there's never, like naked state never comes in. So I think it's not a controversial thing to say that in standard quantum mechanics, testable predictions can be parameterized with what I would call multi-time correlation functions of observables on a state. So a long name, multi-time correlation function of observables on a state. Okay, so let me call those guys. Let me write down what I mean by that. So multi-time correlations. So multi-time correlations, I would denote them by using the following notation. You already recognize what's going on here, right? Tj, k, I minus, k minus, tk, in row. So this is a symbol, okay? What stands behind it is a following formula. So you get trace, you get product, J in the set I plus, J, and I'm sorry, I have to put here a time ordering operator, row, operator corresponding to row, product K, F, K, T, K, and another time ordering, but dagger. Okay, so let me explain. So we have here a set of indices from 1 to n, okay, which numbers timings, Tn, T1, 0, okay. So you have a multi-time, this is a multi-time part, all right. I plus, I minus, those sets are, so you distribute the timings between those two sets in such a way that okay, you just take your timings and distribute them among the two sets of timings. Okay. Fj, operators Fj of Tj. So these are in standard formulation. So these are Hermitian operators in a Heisenberg picture representing a sequence of observables we want to correlate. Okay. So this is multi-time correlation of observables, which are represented by those operators, which I will immediately write it in the form that will be useful for us later. Fj eta, Tj phi j. Okay, with them. So, there's some basis corresponding to eigenvectors of this operator Fj, and it has eigenvalues, right? So here you have a row. This is the state, correlation function of observers on this state row. And you take operators on the plus side, multiply them and order them, so that time ordered from the earliest time closest to row to the latest time furthest to row, and the minus is for you again take operators, order them, but then take you order them in reverse. Okay, so the latest time is on the end on the right hand side, and the earliest time is next to row. Okay. So this kind of guys, using this, you can, for example, I mentioned the linear response theory, which uses the correlation function this kind of correlation function. So the commutator of observable at different points in time. So in this language, this would correspond to F plus T2, F plus T1 row minus okay, F minus T1, F minus T2. Okay, this is just to show that whatever you can think of in any calculation doing quantum standard quantum mechanics, you can parameterize it with this kind of some function of this kind of multi-time correlation functions. Okay, and so my statement is that these guys testable predictions in standard standard formulation, even though it has state as like a central object, testable predictions have to go through this kind of multi-time correlation calculation. Okay, you feed your state into this kind of thing. All right, and I know if someone has examples that would contradict me here, I would love to hear them. But here is my, but once we agree on that, okay, this is when we can show that bitrajectory formulation is in agreement with standard formulation, because it's very convenient that these guys, these multi-time correlation functions, they are actually moments of bi-probabilities, okay? So in bitrajectory formulation, you obtain those guys by taking a moments of corresponding by probability. So in other words, in bitrajectory formalism, correlations are moments. Right, so you can write it plus Tj times k in I minus, this is no good, rho actually equal to minus product 1 to n, and it's a fj plus, oh no, sorry. What's going on? Oh, some weird stuff. Fj plus times k I minus k minus q fn rho tn 0 fn plus fn minus. Okay, so it's a moment, literal moment of biprobability. Of course, one that's associated with the selected observables, right? That's to be expected. But you can also, write it in terms of master B probability, which I will do. Eta T J phi j k I minus fj eta minus tk. So we see where depending on whether it's on the left side or right side of the state, right? This is what's connected to corresponding plus component to minus component of bitrajectory. And there is a initial condition. We can parameterize it like this with eigenvalues of density matrix. A cute way of writing it down. It just exploits the fact that the bitrajectories, they meet at the beginning and the end. So so this square root of rho basically turns into a just rho. Okay. So my claim is here that even though the formalisms are very different, the state is completely, there is no state in by trajectory formalism, and also there is no dichotomous mode of description. If there is no state, then there is no distinction between context of measurement and non-measurement context. So it's whole, the whole cascade of consequences. But even though they are different in such a fundamental way, still the predictions are the same. So we are safe. This is the simply different formulation of quantum mechanics, but the same theory, still the same theory. Okay, we are not inventing something new. We're just rewriting in a different way. This is like Newtonian versus Hamilton formulations. Okay, and this kind of shows this. All right. So this is like a sanity check, right? That we didn't do something completely out of whack. But to finish off this summary and the lecture as a whole, I want to give you like a quick rundown. Okay, so it's what new is offered by this bi-trajectory formulation. What is the benefit of using it, right? Because we know from classical mechanics, like Newtonian mechanics is useful in certain cases. There are other cases where it's better to use Hamilton formulation. The other cases is Lagrange formulation is even better. So we expect this similar thing to happen here. Okay, there will be some problems where, especially some quantum static stuff, where the standard formulation is very good. Nothing. It's good enough. You don't have to do anything more fancy. But there are other problems where it's more natural to use bi-trajectory language. And I want to point to like two big categories of problems, which actually, when combined together, I think form a great argument why a measurement problem is no longer a problem in this formulation, right? Because it's different formalisms. Different formalisms can have different problems, fundamental problems, right? In one formalism, some problem might be trivial or maybe not even exist at all. And when in other formalism, it's like, it's just insurmountable difficulty, like the measurement problem, standard quantum mechanics, as we discussed in the very beginning, is a huge issue. And I want to show that in bi-trajectory formalism, there is a good chance that it's no longer the issue. It's not that it's easier to solve. I think there is just no problem at all. It's very straightforward what has to be done to actually model the measuring device. But let's break it down into those two categories. So category number one is a classical limit. In the trajectory. So, problem of measurement is, we all feel it, and when you think about it, it's almost inevitable to come to conclusion that it's very tightly related to classical limit, right? And in standard formulation, classical limit is something really difficult to grasp to really figure out what has to be done. There are a lot of opinions what classical limit would mean. in different contexts. But the main issue, I think, boils down to the fact that, okay, if you want to talk about classical limit, then, well, the task is to write down a state that could be identified as a state of a classical system. And that's just, I haven't seen like a good universal answer what kind of states correspond to classical systems. There are contexts where it's kind of clear what kind of states leads to what. But like one universal, robust way of thinking about it, it's just unnatural in standard formulation because of the state. Because you focus on states are something that's in classical theories is just not present there. There's something that would correspond to states. So it's like very difficult to trace some path going from quantum state to classical state, because in classical physics there are no states like that. So what to do? But here in by trajectory formulation, it's actually quite straightforward. Okay, because classical theories are unitrajectory theories, right? So there is a master measure on space of unitrajectory, one trajectory. Okay, however, essentially stochastic process, probability distribution on space of unit trajectories. That's some kind of classical theory you are looking at. Okay, quantum mechanics then is clearly not classical because it's bitrajectory. You have a complex value measure on space of bitrajectories. So it's definitely one is not like the other. But you can, okay, so what would classical limit be? Well, if you can make bitrajectory in a collapse into unitrajectory, well, you got yourself a classical theory, effective classical theory, right? This is kind of intuitively clear what has to be done. But there's more caveat here, because unitrajectory theories have this, they have this special property that there's only one observable in there's one elementary observable in each classical theory, right? But in bitrajectory theories, there are infinitely many observables. This is where this space-like coordinate comes in, right? That's why you have a field, space-time field, rather than just time-dependent trajectories. So to really talk about classical limit, you have to do this push forward, change your variables from general any observable to just pick one observable and look at by trajectories of this one observable and look for classical limit in there. Okay, so if we go from our master by trajectory measure and we change our variables and we go to some QF, okay, in the manner that we talked about previously, we can take a look at this guy and ask about classical limit in this context. Okay, and it's like I said, this is very simple, because then the classical limit is when the components of bitrajectory representing this chosen observable. So this is a classical limit for specific observable in the system, not for the system as a whole. If you try to force that eta plus and eta minus are always overlapping, as far as I understand this would mean that it's like a static, uninteresting system. No dynamics can happen, or like this is I think, the only way to make it so. Okay, but there are, once you focus on concrete observable, there are many more options open up to achieve this. So the classical limit, we want to turn a by trajectory into unitrajectory. Okay, so classical limit is when this Q f prime goes to delta, functional delta, so components are the same, and there is, then you have a distribution of this unitrajectory, right? So in other words, the measure of cases when components of this bitrajectory are not overlapping is just 0 or close to 0, right? Because there is, now we have a room to like, strict limit would be when it's exactly 0, only non-zero values are assigned to case when bitrajectories, components of bitrajectory overlap exactly, but you could allow for some epsilon, right? There is quick drop off when they are, start to differ a bit. And you could talk about degrees of classical limit, right? We tend to classical limit, some approximated classical limit, right? And what is cool about this whole formulation that, so this basically selects for the diagonal part of biprobability. But biprobabilities are positive semi-definite measures, okay? And they are normalized. So automatically the diagonal part is a non-negative and normalized function, okay? So whenever you get that off-diagonal parts disappear, you automatically get something that's a probability distribution on the space of unit trajectories, which make it automatically a stochastic process, which make it automatically some form of effective classical theory immediately, okay? So classical limit is summarized. This is how we would summarize the classical limit. It's very simple, and it's a strong statement because it means, if you go to some correlation functions, okay, actually autocorrelation functions, because you just look for correlation of this one observable you have chosen, all those correlations become identical to correlation functions of the stochastic process defined by this diagonal part of this biprobability. So it's really in every possible context, once your biprobability loses all the off diagonal parts, you are really talking about classical theory immediately. Okay, you just branch into effective classical theory in all possible respects. Okay, it just turns into a stochastic process. Your observable starts to behave as a stochastic process from all points of view. So this is pretty robust way of defining the classical limit, and the real challenge is then to show how this shedding of off-diagonal part actually emerges from the dynamics of the system, because your system is defined by Hilbert space and some Hamiltonian, right? This is what generates all the biprobabilities. And in this case, you can add that you also you go to a specific observable, right? So we have Hamiltonian, Hilbert space, and some observable, and is this triplet? Can you find such triplets that actually lead to this kind of behavior naturally? And we actually, we identified like a couple of categories of systems that actually have this kind of behavior. This dynamical emergence of this classicality in this sense. And it's like all the usual suspects you would expect. If you chaotic systems have this kind of behavior, large, massive systems tends to behave like this. Also, systems subjected to specific kind of decoherence also tend to behave like this. So it's like all the systems we intuitively expect to behave classically, you can show that in this, using this concept of by trajectories, by probabilities, you can show that this is actually, this is what you get. They turn into stochastic processes naturally, okay? Of course, sometimes it's with some epsilon, approximated, sometimes it's exact, but you know, you have this freedom, but the robustness of this construction, that this classical limit is when bitrajectory collapse into unitrajectory. It's simple, evocative, and useful. Okay. And when you compare it to the standard formulation, you know, it's way more easier to handle. Okay. So this is like one category of problems that bitrajectories are really good at. Okay. Classical limit. Talking about it, finding it, analyzing it, it's very natural. This is a very natural language because it's bitrajectories are close to unitrajectories, right? Because it's like the next one step of complication, right, above the simple unitrajectories. So this is a very natural language to talk about. The second category is interacting systems. So if you have composite system, so you have Hilbert space made out as a product of two Hilbert spaces, and there is some Hamiltonian AB that has, you know, local part, H. I don't want to confuse it with the this kind of font, okay? Plus, there is some interaction. Okay, so operator that acts in both spaces at the same time. So these guys generate some by trajectory measure, right? But so let's call this consult my notation. Which one I picked? Okay. So let's indicate that it comes from this pair. HAB, okay. So just to remind us, because we will start to fiddle with this. And it's like, because there are two subsystems, we have a, you know, bitrajectory for each subsystem, okay? So you have like a, there is a way to like split the degrees of freedom. Oh, this is what I want to say. So we can write it as, so we have a bitrajectory associated with A and bitrajectory associated with B. The plus, the minus, the plus, epsilon minus. Okay, so it's a big, huge bitrajectory distribution for this like pair of bitrajectories. Okay, so each one representing the pieces, the components of our composite system. Now, sometimes it's or even often, you want to, if you can partition your system into pieces, you want to focus on one piece and like don't worry about the other one, right? So in the language of measures, that would amount to basically marginalizing. Or let's say we want to focus on A, subsystem A, so by trajectory eta plus eta minus. So we would marginalize over epsilon plus epsilon minus, right? To get only measure for eta plus eta minus, measure corresponding to A. So you can marginalize, or you can use the law of total measure and express this marginalize by probability using conditional measures. Okay, it's like with probabilities. You can marginalizing like multivariable probability. You can express it as a I will write down. So if we take Q associated with A, so for plus minus, law of total measure, total probability, sometimes it's called. You can write it as a conditional plus minus conditioned on epsilon plus epsilon minus. So this would be a conditional by trajectory measure. It's conditioned on by trajectory corresponding to B, and you average it times Q HB HB epsilon plus epsilon minus. Okay. So this is like this is just, we are just using a measure theory, just maths. Okay. You have multivariable distribution, and you want to marginalize it over one of the variables, which you can then express through conditional, as in like average over conditional probabilities. It's like basic stuff. But this construction is useful because this guy here, okay, this is a by trajectory measure of free system B. Okay, it's generated by a Hilbert space HB and a Hamiltonian HB, a free Hamiltonian. You know, this guy. I didn't wrote here that this one is also generated by some Hamiltonian, because once you do them, once you marginalize, it's no longer the case, typically. If they were independent, then yeah, this would just reduce to, so if there was no interaction, if this was zero, okay, this guy would be, you could say that it's generated by by Hilbert space A and Hamiltonian H. But because of interactions, because of this conditional by probability here, it's no longer true that you can like find the Hamiltonian that would be responsible for generating the stuff on the left-hand side, okay? But this guy here is like a by trajectory of isolated system B, okay? So of course the whole difficulty here is now to calculate this kernel here, this conditional probability. And we actually did one example on previous lecture. We found we calculated this kind of kernel. Let me scroll up to it. Oh, this is the corresponding stuff, okay? Basically, so this is like a discrete restriction of of master measure for eta plus eta minus, and this would be the free by trajectory measure for B, and the kernel is it's a thing you can calculate. okay, depending on the context, what you are doing. So it's, you know, it's kind of mysterious, but it's in practical scenarios, it's not like completely out of whack to actually find what it is. But the key thing is that you have you can compartmentalize your problem. So this is like an open system kind of scenario. So you're looking at A, which is coupled to B, open to B, but you can like calculate what's going on, but using the properties of isolated B, okay? So you don't have to worry about how B is changed by the interaction with A. You just worry about how A is changed by interactions with B, okay? And this is just a consequence of using the formalisms that base on measures, of trajectory measures, be it uni trajectories or B trajectories. That doesn't matter. So taking this with us, I want to spend like last couple of minutes to take 1 and 2 and combine them together, okay? Because you can, so you understand how to describe two quantum systems interacting with each other. But now you can think, okay, what if one of those systems goes to the classical limit? In other words, how can I attack the problem of quantum classical hybrids? Okay, and this is pretty important stuff if you think about a measurement problem, right? Because you would expect that quantum classical, I mean, measuring device would be quantum system that interacts with other quantum systems, the system that is measured. But this system, and we are looking at this system A, that's A will be the measuring device, and it goes to classical limit. So it would be this kind of classical quantum hybrid. But you can have also the other way. A is left as a quantum system, but B goes to classical system. So we have three classical quantum hybrids. Okay, so A, you can have I'm almost done. It's just a couple of last remarks here. Okay, so first let's consider a situation where we have the B part goes to classical limit, okay? So to go to classical limit, rather than thinking about, you know, epsilon, we have to pick a concrete observable. So let's say that interaction VAB is actually breaks down into this kind of simple form, and then it's natural to pick observable VB, okay, as the one observable we want to focus, because actually the conditional probability, because this is how A experiences B, it actually does not experience the whole system, it just experiences this one observable. And this is actually the case the formula I showed you for the concrete example of the conditional probability, this was for this case, where there was this kind of interaction, so there is VB was the choice to make. So let's write it that it's conditioned by observable VB. So you have plus minus conditioned by V plus V minus VB V plus V minus. Right. So this is a push forward measure of bitrajectory measure for B as a whole, and you change variables to just focus on observable VB, okay? dv plus, dv minus. And of course, what is the classical limit? Well, this guy goes to of diagonal parts disappear. So classical limit would be VB minus VV P V B V. Okay, so both B trajectories collapse into unit trajectory. Okay, and now if we jump into the inspect the formula again, we are here. Okay, so this is the conditional probability. Okay, and you look, the conditional probability looks like a pi probability, but the projection operators evolve with this funky Hamiltonian that has this correction based on the value of components of B trajectory. But when your B trajectories collapse into one unit trajectory, okay, you have the Hamiltonian, the effective Hamiltonian on this side and this side becomes the same, okay? So what it turns into, so this is, if this is the case, when the B subsystem is in class, the VB observable behaves as, is in classical limit, this effectively turns your, turns everything into a, how to say it? So you can express the dynamics in A using a Hamiltonian that's coupled to external potential represented by a stochastic process, VB. Okay. So classical limit defines a stochastic process V, okay, which now couples to your system. And from the point of view of systems dynamics, system A dynamics, it looks like your Hamiltonian has been modified. So you go from HA to HA plus VA operators time this unit trajectory of the stochastic process. Okay, and it can be stochastic. I mean, there could be randomness there, but depending on what this classical limit actually looks like, this could be a deterministic process as well. Deterministic processes are just special case of stochastic processes. So this kind of hybrid explains the origin of external fields in quantum mechanics. Okay, so they come from interaction with quantum systems, but quantum systems that just go to the classical limits. Okay, and if this is the case, then you can just like forget about B and effectively treat A as isolated but coupled to some effective potential that might be noisy. Okay, and how noisy it is, how does it look exactly? It depends on the properties of the B, which we just eliminated in this limit. Okay, so that would be the, I'm almost done. So B, you could have the other way around. So the case small b is where you leave B subsystem as quantum, but you go to classical limit with A. This is what I would say, this is like a prototype of a measuring device. Okay, so this would be, so if you pick some observable FA, right, then you would FA conditioned by VB, HB, sorry. Prime epsilon plus epsilon minus u hp hp and classical limit that would just go to some f times delta in prime. Okay, so you get what this means, that you get a classical theory where the probability for unit trajectory, which you can, it just looks, from every point of view, it looks like a classical, just stochastic process, so a classical system, but it's actually conditioned by probability, full by probability of the system it is coupled to, okay? So then you can treat this conditional probability here as a kind of filter, okay? So it takes this by probability, which may be the system you want to measure, and translate it into a stochastic process, which you can treat as a classical system from this point. It's just classical theory, but conditioned by this weird quantum thing, right? And depending on what is the form of interaction, which then informs you what is the form of this filter here, you will extract some information about those bitrajectories here, okay? And it's immediately apparent that you will lose some information here, right? Not only you have to like compress two trajectories into one, right? But also there is some, this could be done like, you know, so you get a multi-component trajectory maybe, but there is a nuance of complex value measure here that, you know, there's some interference and stuff like that. And you have to compact it into a probability distribution, positive probability distribution. You have to lose some information, okay? So classical observer who couples to classical F, this process F, cannot have the full picture. This filter here cannot be just one-to-one, okay? There has to be some loss of information. What kind of information you extract? Well, that depends on the details of interaction. For some type of interactions, we would expect to get our you know, Born rule, the probabilities, phenomenological probabilities we're talking about. But for some other form, you get something different, some maybe monitoring scenario, or maybe someone nobody thought about yet. But you have the fact that you translated your quantum system into something that's effectively like a classical theory. This just, you know, allows you to model measuring devices without much effort, basically. I mean, it's like there's no longer a conceptual issue with like switching between modes of description, because this is just a limit, well-defined limit of just by trajectory distribution. So I think this is still work in progress, giving the concrete models here. This is something I'm working on right now, let's say, but I believe that it has legs. Okay, there is no conceptual problems like Heisenberg cut here. Okay, this is the main thing, and because of that, this quantum classical hybrids are very natural. And once you have natural classical quantum hybrids, I don't expect non-technical problems anymore, okay? And we are running out of time, so I would love to ramble even more, but I think it's time to finish this lecture and actually whole course. And you know, check out the paper in on the website. I will update it soon to reflect actually the notation and stuff we're talking about here. But yeah, that's that's the end of the journey. Okay, so we started from anatomy of physical theories, theory of theories. Then we went through phenomenological observations that are characteristic to quantum systems. We noticed it quirks, it with behaviors, how non-classical it is. Along the way, we learn about what classical theories actually are, unitrajectory theories. It's also good quantum of information to have. And, we collected our experiments, the interference stuff, the Zina effects and all those things. And we managed to deduce, by probabilities, Hilbert space representations, unitary operators, basis changes, Hamiltonians, it all came from there. There were a couple of forks in the road along the way, but I feel we managed to underline where they are. And the paths we chose led to something that didn't end in the dead end, but we progressed to this. We found the master object, the bitrajectory picture, with these nice properties of classical limit and interactions, which then you can combine into classical quantum hybrids, which gives, there is some power in it. If you want to see more use of this particular property, invite you next semester. I'll be talking about theory of open systems. We'll be basically talking about this, okay? And we'll be using the bitrajectory stuff to actually build the theory of open systems. So it's not just pure theory and abstraction. There is concrete use cases and actual calculations you can do with all this formalism, and it leads to interesting results. Okay, so I think I will finish on that. I don't know how to end it, so I will just stop recording.